All right, guys, this video is going to start our discussion of probability. We're not really going to do the sections in the book as they're listed. I'm just going to kind of talk for a while and cut it off, and then we'll resume with video number 2 later. So there's a couple important terms that come from section 6.1. The first one's random, the second one's probability, and then independence. Random, it's an important word for us. It doesn't just mean, when somebody says something off the wall, you say, "Oh, that was random." It doesn't mean, as our book says, haphazard or unorganized. Random means basically this. There's the official definition on 332. But my definition is going to be the short term is unpredictable, but the long term is predictable. So whatever event's going on, whether it's rolling dice or picking cards or playing roulette or whatever it is, we have no idea what's going to happen in the short term. You can calculate which outcomes are more likely to happen, but any of them are possible. Any of the numbers on the roulette wheel are all possible. We're going to do a little calculator simulation of a spinner. Anything's possible. I have no idea what's going to happen. Yet in the long run, I can tell you depending on how long I watch, with some degree of certainty, what's going to happen percentage-wise in the long run. The official definition says we call a phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. You should make sure you check out those definitions on 332 because there are, a multiple choice question might word the definition this way, and that would be the correct response when something that looks like it makes a lot of sense would be a wrong answer. So check those out, 332. Actually, I put that there. But I just wanted to put it in my own terms for this particular video. Probability of any outcome, according to this definition, is the proportion of times the outcome would occur in a very long series of repetitions. That is, the probability is a long-term relative frequency. So let's see, let's call it the proportion of times the event, and the event is another word that's important in this section, happens in the long run. All right, so we would all agree, I believe, that the probability of flipping tails on a coin is 50-50, or 1 out of 2. And we know that because there are 2 sides, and one of them has tails on it, so there's a 1 out of 2 chance. But technically speaking, why is it 50%? Who says it's got to land on heads and tails 50% of the time? Well, if you start flipping a coin a lot of times, then it's going to happen 50% of the time. It's going to approach 50% in the long run, which is why we are safe to say that the probability is 50%. All right, it's the proportion, it's the long-term relative frequency, meaning, just keep on trying and watch it get closer to 50%. There's a good diagram on 331. It shows flipping a coin. I'll let you check that out. Basically what it does is, we have 50% here, and then we've got the trials going, and they start out with it spread out like 1 trial, 5 trials, and then they get into 100 and 1,000, and they kind of change the scale up on us. But what happens is with 1 trial, it's either 100% or 0%. Let's say it started out at 100%. Should put that there. And then with 2 trials, it's either 50% or still at 100%. So say it got down to 50. Anyway, this line kind of bounces around for a while, and every time it narrows in, it zeroes in on 50%. That's how we can say the probability of flipping heads or tails, either one, is 50%. I want to show you a little demonstration on the calculator. One of the apps in your newer calculators is called ProbSim, Probability Simulator. You can go in, they've got a spinner, they've got dice, coins, all sorts of things. In the settings, you can change the spinner to where it's not even even sections. All right, so if I spin this spinner, I have no idea what it's going to land on. All right, it's 1, which was my most likely outcome, but it could have been anything. So I'll go again. I'll do a +1 to spin one more time. See if I can get, I got 1 again. So I have zero idea what it's going to be from spin to spin. But a random event means in the long run I can predict what's going to happen. So my magic prediction is this. If I push +50, it's going to approach 1 being the tallest bar, 2 being half that size, and 3 and 4 each being half the size of 2. So we're going to have a little stair step down with 3 and 4 both being tied for the smallest step. Now, does that mean that's what has to happen perfectly? No, but I'm betting you, because I know what the spinner looks like, that it's going to look similar to that. So it looks like we had a lot of 4s at the beginning and 3s are trailing behind. But it started to get, it started to form what I was talking about. The 1s are a little ahead, the 3s got a little ahead of the 4s, but let's do +50 again and see what it looks like. So you should see as time goes on, the 2 should start creeping up. It forms this graph in terms of whatever the tallest bar is. So the closer or the more we do this, keep adding on spins, it should start to work out the way it should. We'll talk about what's called the law of large numbers, which basically says if you do something enough times, it works out the way it should, which is why I was pretty confident in describing what graph was going to happen. All right, short-term unpredictable, long-term predictable. I still am a little ahead of the 3s with the 4s, and it doesn't look like 2 is quite half as big as 1, but it's starting to work itself out. All right, this is a random event. All right, so that'll be the last one. And the more I did it, the more these bars would get the way. That looks pretty good right there. The 3 and the 4 evened out. And after, I don't know how many spins that was, 200 maybe something, you can tell what happens. So this is just a good, it's kind of the same as this coin flipping deal. It's going to get closer to those percentages. All right, when I say the probability of flipping or of spinning a 4, in this case, is 1 out of 8 or 0.125, that's what that means is if I try it enough times, it's going to get close to 0.125. It's going to approach 0.125. Okay, so let me get rid of that. Independence basically means one trial doesn't affect the next. All right, when you flip coins, that coin doesn't remember what it's landed on. The heads tail stays at 50%. When I spin this spinner, it doesn't matter what the first spin is. The second spin still has a 50% chance of 1, 25 of 2, and 12.5% each, 3 and 4. Those are independent because the spinner doesn't remember where it went. All right, I'm assuming that when I flick the spinner, it's set up to be random. I'm sure it is in the calculator. But it's the same idea with, with roulette. I've heard that there's this board in a casino where they tell you what it's been in the past, 15 or so spins, and they've got, red on one side, black on the other side, green in the middle, but they'll do like, it was 22, then it was 5, then it was 7, then it was 15. Than 17. I've heard when they started putting those boards in, the amount of money they made on roulette just skyrocketed because people will look at that board and they will make their bets based on what it has been. They'll say, oh, it's due. If this is what I see and I've got 4 black rolls in a row, maybe I'm saying, well, it's got to be red next time. So I'm going to bet my money that it's going to be red. Well, that marble on the roulette wheel has no idea where it's been. It's no more likely to be red or black based on that little thing there. But people just study it like it's, like it has something to do with what's going to happen next. And it's, just all entertainment. Maybe they just think it's fun to watch. But it has nothing to do with what's going on next because those are independent. All right, so let's move on to a couple more terms. These are actually from section 2. Let's start with sample space. Sample space is basically, according to your book, it's the the sample space of a random phenomenon is a set of all possible outcomes. So let's just call it that, the set of all possible outcomes. And this is going to depend on how you define your what's going to be called a random variable. You know, if your variable is let x be the result of a roulette spin, then it would be 0, 00, 1 through 36, as you remember from our roulette simulation. If your little miniature experiment is a coin flip, then your sample space is heads or tails. If the experiment is I'm going to put everyone in this class's name in a hat and draw 3, and everybody gets a Snickers bar, then the sample space would be everybody's name in the classroom. All right, it's every way that it could go, that a trial could go. They also define event. Event is just something happened. You know, according to the book, it's any outcome or set of outcomes of a random phenomenon. That is, an event is a subset of the sample space. It's just what happened. I don't even really want to define this one. If I flip a coin and it lands on heads, the event was it landed on heads. But I just want you to, be aware that they'll use the word event in questions and in the text, and it doesn't mean anything special. It's just something that happened. They also define probability model, a mathematical description of random phenomenon consisting of two parts, a sample space and a way of assigning probabilities to each. That's also just kind of a general term that I'm not going to worry about defining. We can read about it in the book later. So the next important idea is the multiplication rule. And they also talk a little bit about tree diagrams. We're going to get into some more tree diagrams later, but they introduce it with multiplication rule. That basically just means if there are 5 ways to do the first part and there are 10 ways to do the second part, then there are 50 ways that both parts could go. Multiply however many ways it can happen. So let's say, 3 coin flips. How many ways could 3 coin flips happen? How many sequences of 3 H's and T's are there, basically? You could list them really quickly, but, 2 times 2 times 2. How many ways can the first coin flip go? Times the second, times the third. There are 8 ways it can go. And they introduce this with tree diagrams because that's just a kind of visual of the multiplication rule. My first flip could be heads or tails. Second flip, heads or tails. And third flip, heads or tails. And so what you create, if your experiment is 3 coin flips, then what you make out here is a list of all ways that they could go, which, if you remember from 2 minutes ago, is called sample space. HTH, HTT, THH, EHT. You get the idea. This is just a nice basic sample space. It's more complicated than 1 coin flip, but it brings together all of our things. The tree diagram, the multiplication rule. Why are there 8 things in the sample space? Well, there were 3 trials, or 3 separate parts of the trial, and each one had 2 possible outcomes. So that's called the multiplication rule or the multiplication principle in our book. All right, so the last thing. Replacement, non-replacement. This kind of applies to a deck of cards. And really, I just want to make you aware that it's an issue. Replacement versus non-replacement. So this means pretty much this. If you're going to draw 2 names from a hat, or you're going to draw 2 cards from a deck of cards, the second probability might depend on what your first one was if you didn't put the first card back. Okay, the probability that I draw 2 hearts depends on whether or not I put the first heart back. So if I put it back, then it's just the same. Those are independent trials. If I do not, then that's dependent because the deck is different because one of the cards is missing. All right, so that's really all. I don't want to write too much about that one either. I want to cut this one off at my 15-minute check. So That's the start of my most favorite topic, probability. And I will see you in class. I'm out.